Today we're going to practice some linear algebra problems. Let's jump straight into it. The first problem asks us to consider a spreadsheet of numerical data with 3 columns, and the third column is equal to the sum of the first 2 columns. We're asked to find a basis for the span of the 3 columns of this matrix, and also find coefficients of each column with respect to that basis. Since the third column is equal to the sum of the first 2, it's in their span. So the 3 columns together are linearly dependent. Therefore, they don't form a basis. However, we can always form a basis with the same span by going through the columns one at a time and discarding any columns we encounter that are in the span of the previous ones. So in this case, columns 1 and columns 2 will be kept, and column 3 is in the span of the first 2, and so it will be discarded. So we can say that the first 2 columns form a basis of the space spanned by all 3 columns. To say what the coefficients of the 3 columns are with respect to this basis, we just need to say how many of each of the 3 columns to use in a linear combination to achieve that particular column. So for example, the coordinates of the first column are 1, 0, because we should use 1 of the first column and 0 of the second column if we want to make the first column. Similarly, the coordinates of the second column are 0, 1, and the coordinates of the third column are going to be 1, 1, because we need 1 of the first column and 1 of the second column to make the third column. The second problem asks us to find the rank of the linear transformation which maps each vector to the closest point on the line y equals 2x. So if we take a look at this picture, what we can see is that every point in the plane gets mapped to the line y equals 2x by this map. Certainly points that are off of that line don't get mapped to, and every point that's on the line does get mapped to. So this line on the right side of the picture here is the range of the transformation L. And to recall some definitions, we can say the rank of a linear transformation is the dimension of its range, and the range here is a line. And a line has 1 dimension. If we want to break that down a little bit though, the dimension of a vector space is the number of vectors in any basis of that space, and a line is spanned by a single vector, any non-zero vector in that line, so its dimension is 1. In this problem, we're going to explore what happens when we intersect 2 vector spaces in Rn. So for example, in R3, which we can visualize, suppose you have 2 lines through the origin, v and w, so 2 one-dimensional vector spaces. Typically, those 2 lines would intersect only at the origin, and so you can certainly have a dimension of 0 for the intersection. If v and w each have dimension 2, then you'll necessarily have at least a line of intersection. There's not enough space in 3 dimensions to fit 2 planes that don't intersect in at least a line. So the minimum dimension here is 1. If the 2 planes coincided, the dimension would be 2. So those are the possibilities in that case. To think about what's going on in higher dimension, we can't visualize things anymore. We have to think about bases. So we have 2 subspaces that have dimension 4 and 8 in R10, and we want to know the possible values of the dimension of v intersect w. And the first observation is that the intersection of these 2 vector spaces can be no bigger than the smaller one. So certainly you can't get a dimension more than 4. You're already 4-dimensional at v, and if you intersect it with w, you could lose some vectors, but you can't gain any. So the maximum dimension would be 4, and in fact, it's not so hard to achieve 4. If we suppose that we have a basis of R10, so let's just give some names to that basis, v1, v2, v3, up to v10. We can make a 4-dimensional space and an 8-dimensional space with the property that intersecting them leaves the 4-dimensional space. So we can define V to be the span of the first 4 and W to be the span of the first 8. Then intersecting, so clearly in this case, V is a subspace of W, so when we find the intersection of the two, that's all the vectors in both of them, we're just going to get V again. So we can definitely get a dimension of 4. We can't get a dimension larger than 4. So let's try to move down from 4. If we modify this story by just sliding the vectors over, so for example, instead of V1 up to V8, we can do V2 up to V9. Then the intersection is going to be, the intersect W is going to be the span of V2 through V4. And that has dimension 3. And likewise, we can slide over again and go from V3 to V10. And that's going to be dimension 2. And we're out of space here, so there's not an obvious way to get a dimension of 1. And it's suggested in the 3-dimensional case where we saw 2 planes intersecting, and you have to get at least a line out of that, that maybe you run out of space on the bottom end and you actually can't reach certain low dimensions. And that's the case here. We can't prove it by continuing along these lines because we're building vector spaces here by essentially just working from a single basis and grabbing vectors from that basis as we please. And maybe someone could construct a different example through another approach. So to show that there really is a lower bound here, what we want to do is apply the multiple extension principle. So the multiple extension principle says that if we have a vector space which is an intersection of 2 other vector spaces, that's V intersect W here, we can extend that basis to a basis of V, and also we can extend it to a basis of W. And if we do that and we take all of the vectors in the original basis together with all the vectors we tacked on separately in the 2 bases, one of V and one of W, together, this compiled list of vectors forms a linearly independent set. We can use this idea in this instance to show that we can't get a 1-dimensional or a 0-dimensional space as an intersection of an 8 and a 4-dimensional space in R10. Because if we let D be the dimension of the intersection, then the dimension of V is 8, so there are going to be 8 minus D additional vectors here. And sorry, I think V was the 4-dimensional one. Actually, I forgot. Let me look back. Yeah, V is 4-dimensional. So there's going to be 4 minus D vectors there that get added on, and there's going to be 8 minus D vectors here. And we can take these 3 numbers and add them up. That's going to be the total number of vectors in this linearly independent list. And we know that that sum can be no bigger than 10, because the whole space that they're in, R10, is 10-dimensional, and there can't be more than 10 linearly independent vectors in a 10-dimensional space. So if we solve this inequality for D, what we find is that D is actually at least 2. So we showed how to get 2, 3, and 4. We showed that we can't get more than 4 or less than 2. So that's it. Final answer, 2, 3, 4. In this problem, we explore how rare rank deficiencies are, depending on how a matrix is generated. So if we generate a matrix by choosing uniform random entries, then the rank is always going to be as big as it possibly can be based on the shape of the matrix. So if we generate a 7 by 5 matrix, let's take a look at what one of these matrices looks like. Oops. You see it's just random numbers between 0 and 1. These are always going to be linearly independent. And that makes sense geometrically, because if you think about starting with this first column, it's the probability that it's going to be the 0 vector is 0. And then this column, the probability that it's going to be perfectly parallel to that one is also going to be 0, and similarly as we move through the columns. Even after we have the first two, the third one, the probability that it's in the plane spanned by the first two is going to be 0, because there's loads of additional space for this vector to be pointing in, and it's just too much of a coincidence for it to be pointing in the same direction as either of these first two or a linear combination of them, and so on. And so we can use this array comprehension to run that experiment 10,000 times, and we find, sure enough, that all of them have rank 5. So what we can do to make this a little more interesting is use integer valued random variables. So, random entries. So if we make zeros and ones, then now there's some chance of getting exactly the same vector again, or some other vector that's a sum of some vectors that come before. There's still a good chance that it's going to be full rank. In this case, it is rank 5. But can run the experiment a bunch of times and see what we come up with, and sure enough, even with 10,000 runs, we see some 4s and some 3s. And if we want to check how many 4s and 3s we tend to get, we can use the count map function, which comes from statspace, and that's going to tally things up for us. So instead of throwing away duplicate entries like set does, this is going to keep track of them for us and see how many there are. So there's about 8,400 out of the 10,000, so about 84% are 5s, but there's quite a few 4s and there's some 3s as well. And you can even get some 2s if you run more. There's about, in this case, 5 2s out of 100,000. So the point is that it happens not terribly infrequently that with this particular rule for generating new entries, you happen to get one that is in the span of some previous ones. So let's put this down here. Okay, in this problem, we're given 3 vectors, and we're told that they meet at right angles to the origin, which we could check by computing dot products between the pairs. And we're asked to find coordinates of a particular vector with respect to that basis. Now, the first one we can get just by inspection. We can look and see that if we add 2 of these and 2 of these, then we get 4s in the first 2 coordinates, and the third coordinate cancels, and we can just take 0 of the third one. So 2, 2, and 0 are going to be the coordinates of this vector with respect to the spaces. But then this one is not so nice to just eyeball, so we have to think about it a bit more. And this is because of the right angles here, this problem is actually significantly easier than the general situation where you don't really know anything about these 3 vectors. So let's take a look at some of the math and then come back and do some calculation. So if C1, C2, and C3 are the coordinates of a particular vector, let's just call it V for now, with respect to a basis U1, U2, U3, let's call it, then there's a dot product trick for figuring out C1, C2, and C3 directly from V. And we're going to be assuming here that these are orthogonal. So any pair of them, if you dot, you get 0. Then what happens is that C1 U1 plus C2 U2 plus C3 U3, which is going to be equal to V if C1, C2, and C3 are the coordinates. It has the property that when you dot it with U1, what you get is C1 times U1 dotted with itself, that's the squared norm of U1, plus U1 dotted with U2 and U1 dotted with U3, each time C2 or C3. The thing is, both of those are 0 because each vector dotted with a different vector in the list is 0. So if we just dot u1 with v, we see that what we get is the coordinate that we're interested in, c1, times the squared norm of u. So that suggests a strategy for coming up with the coordinates that we can calculate easily. So let's come over here. We have our array of 3 vectors here, and I want to do an array comprehension over that. So for each vector u in that basis, what I want to do is calculate the dot product, which is u backslash c dot, and I hit tab to get the dot. And I can just dot with this vector 4, 4, 0 first. And then we'll switch to 3, negative 2, 7. And it gave me 8, 8, 0, which is incorrect. It should have been 2, 2, 0. And what I can see is that I forgot to divide by the squared norm of u. And that gives me 2, 2, 0. And then, of course, we can just do the same thing with 3, negative 2, 7. And I get the coordinates with respect to that basis. We also could have solved this problem by just setting up a linear system. We could say c1 times this vector plus c2 times this vector plus c3 times this vector is equal to this vector, and just tell Julia to solve that linear system and we would get the same result. The advantage of doing it with dot products is that we can get each coordinate with a single calculation instead of having to do a solve of a system of equations. So this is another theory problem. We're asked to show that A transpose A and A have the same null space. So in other words, we want to show that if A maps a vector to 0, then so does A transpose A, and conversely, if A transpose A maps a vector to 0, then so does A. So one of those directions is much easier than the other. If A times X is equal to 0, then we can multiply both sides of that equation by A transpose, and we get that A transpose times AX is equal to A transpose times 0, which is 0. So that direction is the one that requires less ingenuity. We just make a substitution of AX being equal to 0, and that's pretty much it. The other direction is a bit trickier. So if A transpose A times X is equal to 0 vector, then what we're going to do here is multiply both sides of this equation by X transpose. So on the right, we're still going to get 0, but on the left, we're going to get X transpose. And from there, we can say that actually AX transpose times AX is equal to 0. And that works because transpose distributes across multiplication, but reverses the order. So we're basically unreversing here. And then a vector transpose times itself, that's the same as saying that the dot product of that vector with itself is 0. And a vector dots with itself to give 0 only if it's actually 0. So that's what we wanted to show. If A maps X to 0, then so does A transpose A. And if A transpose A maps X to 0, then so does A. So they have the same null space. And since the rank nullity theorem says that the rank plus the nullity is equal to the dimension of the domain, that means that their ranks are also equal, since A transpose A and A both have the same domain. Okay, problem 7. A orthogonal complement of the span of the columns of matrix A is equal to the blank of blank. So we're trying to fill in the first blank with range or null space and the second one with A or A transpose. The idea here is that we want to encode the idea of orthogonality to the columns of A. So A has some columns, let's say A1, A2, and A3. And we want to somehow represent the idea of being orthogonal to A1, A2, and A3. You can transpose A so that you turn these columns into rows. And you can think about multiplying this matrix by some vector x. And the result by the product formula is going to be the dot products of the rows with this vector x. And these are all going to be 0 if and only if x is orthogonal to every column, if and only if x is in the null space of A transpose.